Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study revision of deflection of beams. In the previous session, the part 1, we covered what is the governing equation. This is the second session, part 2. Deflection of beams. Now, we have covered in the previous session what is the governing differential equation of bending moment or governing a differential equation of the beam. And we used, there are various methods are there, double integration method, Macaulay's method, moment area method and conjugate beam method are all different various methods to calculate the slopes slope and deflections of a beam. In this session, we are going to find out what is the deflection, slope and deflection of a cantilever beam subject to a concentrated load at a distance of A from the fixed support and uniformly distributed load, etc. So in this session, in the previous session, we covered a cantilever beam subjected to point load. What is the slope and deflections? But in this session, we are going to do more cases. That is a cantilever beam at a distance of A subjected to a concentrated load. The span of the beam is L, point A and point B. What is the slope and deflection at point C? What is the slope and deflection at point B? And the next case we are going to study, a UDL is being acted toward the span of the beam. What is the slope and deflection for a beam subjected to UDL at the free end at the middle point? Or next case, we are going to study in the case of simply supported beam, in the case of cantilever beam, the UDL is acting partially at a distance of A. The origin of the distance is from free support, but the length of the beam is L, span of the beam. And the next case we are going to study here, it is at a distance of A, but it is the point B and it is the L. And one more case, only without no UDL, no point load, only moment is acting either clockwise or counterclockwise. It is for a span of the beam L. And finally, these are the cases, the UVL is acting throughout the span of the beam. Again, it is L. So these are the cases, 5 cases we are going to consider here and derive the slope and deflections equations for these cases in this session. Now, begin with a concentrated load not at a free end. It is at a distance of A from the fixed support. Here the fixed support, here it is the source, that is the origin of the distance. That is what we consider here, at a distance of A from fixed support. And the span of the beam is L. And where it is A and it is B. The load is acting, the constant load is acting W at point C. Consider a section X at a distance of fixed support. We need the bending moment equation for this concentrated load and cantilever beam at this point we want. That means W times A minus X. A minus X, this distance. Now let us find out the bending moment equation at a distance of X. That is negative of W times A minus X. Equate this M equal to EI times d square y by dx square. Then apply the boundary conditions, integration, first integration, second integration, and calculate the constant of integrations. Calculate the constant of integrations by using boundary conditions. Okay, now after that, now we already derived the equations in the previous session, that equation as the slope and deflection for this case also obtained by replacing L by A. Now dy by dx equal to minus W by 2EI times 2AX minus x square, and deflection y equal to minus W by 6EI times 3AX square minus x cube. Now at x equal to, at C we want, substitute x equal to A in this equation, in these equations, that is the slope at C will come, that is dy by dx at C, that is minus W A square by 2EI, and the slope at C, the deflection at C, that is minus W A cube by 3EI. That is, these are the values at a distance of A. That means at a point C we calculated the slope and deflections, but we want the slope and deflection at the free end. How to calculate the slope and deflection at the free end? How to calculate? Now here the beam will bend because of that concentrated load up to A to C, it will bend, but C to B it won't bend. The bending moment remains constant. The bending moment remains constant means it will be subjected to pure bending. The shear force is 0. Now the pure bending at that point. So how to calculate the deflection where the pure bending, constant bending moment? Here, if you consider in this figure, this is the curve. This is the bending deflection curve up to point C, that is the point D, it is the point B, HG here. We want this distance, that is the GF, is the total, this is the GF with the deflection from D to H. But at point B, the deflection equal to HF. That means HF means HF equal to HG plus GF. We know HG value, that means that is the deflection at E, that means deflection at C, that is a DE. The DE equal to HG. So DE equal to HG, we know the deflection at point C. But we want to find out the deflection at B. So deflection at B equal to sum of deflection at C plus GF distance. That GF distance comes, this is the slope angle. So we want GF equal to, this slope is theta C. That means GF equal to slope times EG. Slope times EG. Alright? Or the slope times EG. Okay, slope times EG. What is the slope? What is the slope at C? We already calculated at point C. That is WA square by 2EI. WA square by 2EI is calculated. Now let us substitute deflection at point B. Deflection at point B equal to deflection at point C plus GF value. This is the equation. Deflection at point C, that is negative of WA cube by 3EI. Now point GF, that is GF equal to, as I mentioned here, theta C times EG. What is theta C here? That is slope at C, that is negative of WA square by 2EI times GE. What is the value of GE here? That GE is nothing but total L minus A. That is GE equal to L minus A. So this is the deflection at B. Now deflection at B is calculated. Now this is the deflection at B. And here the slope at B, that is slope at B equal to minus WA square by, that is slope at B equal to slope at C, because slope at B and slope at C both are same, because it's the same inclination. There is no load acting at point B. The same slope will continue unless until another load acts at point B, again the slope will be changed. So the same load at this point, the slope is at W at C is acting, that the slope will continue. Next load is going to be acted, where then again slope will be changed. Now deflection at C. The deflection at C is WAQ by 3EI. Deflection at B, this is the value, negative of WAQ by 3EI minus WA square by 2EI times 1 minus A. Now we want a deflection if W is the at midpoint, that is x equal to L by 2. Substitute in the equation where A equal to L by 2, then we will get it here. That means W times L by 2 whole cube by 3EI plus W times L by 2 whole cube A square by 2EI times L minus L by 2, that is L by 2. That is 5 times WL cube by 48 EI. 5 times WL cube by 48 EI. This is the one we calculated here. Now next case. The case is that uniformly distributed load throughout the span of the beam. Now this is the case. For this case, if the total UDL is acting throughout the span of the beam, now the origin of the distance is point B. From this origin, we are going to consider the distance x. The span of the beam is the L. The uniformly distributed load, intensity of the load is W, that is small w. From this span, the total load is W times x. It is acting at a distance of x by 2. It is acting at a distance of x by 2. Consider bending moment at a distance of x. At a distance of x, that is small w x square by 2. EI times d square by dx square equal to minus wx square by 2. So integrating this equation, EI times dy by dx equal to minus wx cube by 6 plus c1. How to calculate that c1 constant of integration? At x equal to L, dy by dx equal to 0. Then c1 becomes WL cube by 6. Substitute WL cube by 6 in the place of c1. Then the equation of the slope becomes EI times dy by dx W by 6 times L cube minus x cube. This equation is the slope equation of the case cantilever beam subjected to UDL throughout the span of the beam. Next, if we integrate the slope equation, that is EI times y, EI times y equal to W by 6 times L cube by x minus x power 4 by 4. Then what happens here? W by 6 times 4 L cube x minus x power 4, that is 24. W by 24 times. This is the deflection plus C2. Where C2 is the constant of integration. This constant of integration is going to be calculated. Now, what is the maximum slope? The maximum slope will be occurred at x equal to 0. That is WL cube by 6EI. And the maximum deflection, that is minus WL power 4 by 8 EI, where it is the maximum deflection occurs where x equal to 0. Here, what is the meaning of x equal to 0? It is not at the support. We considered x value, the origin of distance of x, that is a point B from this x. That means this maximum slope and maximum deflected when x equal to 0 means theta b, and it is yb. These are at the free ends. At the free ends. At the free end. At the free end, the maximum slope is W, small w, that is the uniformly distributed load, that is Newton per intensity of the load times L cube by 6EI. This is small w, L power 4b, 4 by 8 EI. So in this manner, we calculated the slope and maximum slope and deflection where at the free end, point B. Now, if we consider the origin is considered distance, the origin is at a fixed support. If the origin is fixed support, then what is the slope and deflections? How it is worked out to be? The slope equal to minus W by 6EI times 3L square x minus 3L x square plus x cube. and the deflection is minus W by 24 EI times 6 L square x square minus WL x cube plus x power 4. Okay, these are the equations, we got it. Now, if we integrate the slope and deflections, now we got it as W x power 4 by 24 plus WL cube x by 6 plus C2. This C2 is the constant of integration that should be calculated by using the boundary condition at A, that is at point A, x equal to L, y equal to 0. Now x equal to L, y equal to 0, it is at A. Then what is the origin? The origin is point B. Origin is point B. The origin is point B because we considered x here. Now it becomes x equal to L. X equal to L. That is the fixed support, x equal to L. What is the y? X equal to L. What is the y equal to deflection? Deflection at fixed support is 0. Okay, at a distance of x equal to L. Now substitute back x equal to L by using this boundary condition, calculated value C2. The C2 is minus WL4 by 8. Substitute the C2 value here. That is minus Wx power 4 by 24 plus WL cube by 6 x minus WL 4 by 8. Now that is the deflection equation. So the slope and the deflections, if we simplify it further, y equal to minus WL power 4 W by 24 EI times x power 4 minus L cube x 4 L cube x minus 3 L power 4. This is simplified. And this is the slope equation. The slope equation is W by 6 EI times L cube minus x cube. So these two formulas are derived for the case of a UDL. The origin is at the free end, point B, that is the x. And the span is L. Okay. These are the equations. These are the two equations. Now consider another case. In another case, fix a free, there is a cantilever beam subjected to UDL, but the distance, at a distance of A from fixed support, at a distance of A from fixed support, the origin is the fixed support. And x we consider, the origin is the fixed support, point A is the origin, and point B is the free end point. Then how to make it? In the previous case, we consider throughout the span of the beam, we know the slope and deflections at point B. If you want at point B, we have to, at point C we need. So we subtract the total UDL minus deflection of the uniformly distributed load, deflection, minus, if we subtract this point, we'll get it. How to make it here? At a C, dy by dx equal to minus WA cube by 6EI, and YC is minus WA power 4 by 8EI. Now deflection at B equal to, what is the deflection at B? Total minus that one, if you remove it. If you make it WA power 4 by 8EI, deflection at B minus deflection at C, then it comes, that is minus WA cube by 6EI times L minus A. This is a deflection at B. Okay, deflection at B means throughout we make it. Then if you subtract deflection at B, deflection at C minus total minus this portion, then we'll get it deflection at B. Now, next case, in this case, the UDL is acting from free end. Before case UDL acted from fixed support. Now UDL acted from free end. Now that is at a distance of A. This is the peculiar case. How to calculate? So we will consider the throughout the span. In that you will subtract this portion. Then we will get it. What is that? Let us see here. So the slope and deflection at point B can be found by first considering the cantilever beam. Cantilever loaded for the whole span. Loaded for the whole span. And then that is the figure A. Loaded, we consider it. Then deducting the effect of for the span loaded from A to C. Before case A to C we calculated at a distance. So if we deduct from the total to A to C portion, then we'll get a BC portion. AB minus AC, that equal to BC. BC portion. This is the concept we used here. For that, what we did, we applied vertically downwards UDL and vertically upwards UDL. So we are here vertically from this total span minus this portion. If we subtract, we will get the BC portion of the slope and deflection. That is what here. Thus the slope dy by dx equal to WL cube by 6EI minus W times L minus A whole cube by 6EI. So deflection can be found. How we found deflection? For a whole span having uniformly distributed load, that is IB equal to WL power 4 by 8EI. It is downwards acting. Now for the span loaded A to C, it is upwards between. Then what happened? That is W times L minus A. If you make it L minus A power 4 by 8EI plus W times L minus A cube by 6EI times A. Now it is upwards. Subtract from YB, that is WL for 4 by 8EI minus this portion upwards. Then we will get the deflection beam at downwards. That is WL for 4 by 8EI minus W times L minus A power 4 by 8EI plus W times L minus A whole cube by 6EI times A. This is the equation. Okay. The final case of, that's final last but one of cantilever beam. By using, which method we are using? We are using here double integration method. Now here a couple only acting at the end in clockwise direction. Now couple acted at the end in the clockwise direction. Consider the distance x. The origin is point A, that is a fixed support. Write down the bending moment equation, that is EI equal to EI times d square y by dx square equal to minus m. EI by dy, EI times integrating this equation, EI times dy by dx equal to minus mx plus c1 or integral mx plus c1. Now at x equal to 0 dy by dx, what is the x equal to 0 dy by dx equal to 0? Substitute here, then c1 comes. C1 is calculated as 0. Substitute the value of constant of integration in the slope equation. That equation becomes EI times dy by dx equal to minus mx. This is the slope equation. Now integrating the slope equation, then we get it deflection equation. That EI times y equal to minus mx plus c2 minus mx square by 2 plus c2. This c2 is the second constant of integration. It is related to the slope. It is related to deflection and span. So that's why x equal to 0, y equal to 0. Substitute those two conditions in the equation of above equation. Then you'll get the value of the C2. That C2 is obtained as 0, nil, no effect, constant of integration. Then substitute back the 0 constant of integration in the equation, in the above equation. It is obtained. That is the deflection equation is obtained. The deflection equation is EI times y equal to minus m by 2 times x square. Now, at the various values of the x, this equation gives the slope equation, the deflection equation, and this equation gives the slope equation. So, the slope equation, that is dy by dx equal to minus m by times EI times x. Minus m by EI times x is the linear variation. Whereas for deflection, the deflection equation y equal to minus m by 2EI times x square. It is a parabola. Now, the speciality for this case, the slope and deflections are in terms of moment, couple, that is m, not in w, vertical, UDL or concentrated load. It is in terms of couple. That's why dy by dx equal to minus negative m by EI times x. The variation of the slope here, it is a linear variation, whereas the deflection variation is parabola, the deflection varying. And where is the linear variation? The slope varying is the linear and the deflection varies curve. Alright. This is the manner, in this manner we have to calculate the slope and the deflections of the case of a cantilever beam subjected to couple at the free end. If it is clockwise, it is counterclockwise, the equation will be changed. When it is counterclockwise movement, the upward deflection curve comes. Movement, deflection. So based on that, we have to go for it. We calculated here slope and deflection of a cantilever beam subjected to only movement couple at the free end. There is neither UDL nor concentrated load. Now the final case is that the cantilever beam is subjected to UVL, uniformly variable load. This uniformly varying load, it is at zero intensity at the free end, the point A and point B. That's why the origin is the point B. From that we consider the section X. Alright, at a distance of L. Now Wx by L, why we have considered the origin point B? Why we not origin at fixed support A? We are going to learn now in this case. Now for that bending moment at C, point C, intensity of loading at any cross section C at a distance X from free end, that is Wx by L. That is the bending moment at C at a distance C, that is the area, that is a triangle, that is half base into height, 1 by 2 times Wx by L times X. This is the height, it is the base. Times what is the distance of centroid of the load, distance of center of load, that is at a distance of h by 3, that means x by 3. That is x by 3, that is Wx cube by 6L. Equate this bending moment equation at a section X equal to governing differential equation of bending of the beam, that is Ei times d square y by dx square. That Ei times d square y by dx square equal to negative of minus Wx cube by 6L. Now now differentiate this equation once. Ei times dy by dx equal to minus Wx cube, that is x power 4 by 4, that is 24L times C1. Now how to get constant of integration? By using the boundary condition, which should be related to the span of the beam and the slope. That's why x equal to L, dy by dx equal to 0. What is the consideration here? X equal to L means it is the fixed support, because our x is source point is B. X consider this is a source point B. That's x equal to L means x equal to the fixed support, the dy by dx equal to 0. That's why C1 is obtained as WL cube by 24. Substitute this C1 in the equation. That means Ei times dy by dx equal to minus Wx power 4 by 24L plus WL cube by 24. This is a slope equation at a distance of x calculated. If x equal to 0, x equal to L by 2, x equal to L by 3, L by 4, L by 6, and so on up to L, we can find out the slope at those particular distances. Now we are going to integrating the deflection, that slope equation, we'll get it the deflection Ei times y equal to minus W times x power 5 by 120L plus WL cube x by 24 plus C2. The C2 is calculated by using the boundary condition. That boundary condition should be related to span of the beam X versus where? Another one, deflection, where y equal to 0. At x equal to L, y equal to 0. This x equal to L means fixed support, because we consider the value of the section X. The origin of the X is point B. That's a free end. Okay. Now substitute here the C2 is obtained. That is minus WL power 4 by 30. That is Ei times y equal to minus Wx power 5 by 120L plus WL cube x by 24 minus WL power 4 by 30. Now the slope at the slope and deflection at the free end. That means x equal to 0 substitute. X equal to 0 means y equal to minus WL power 4 by 30 Ei. That is the slope. This is the slope. This is the deflection equation. And this equation is the slope equation. Substitute x equal to 0, that WL cube by 24 Ei. That is the slope. Where free end, the maximum, these are maximum slope and maximum deflections. So these are the things we have calculated. What we have mentioned in the starting of the class, we completed those 5 sessions. Yes, let us begin with what are the case studies we have covered here. Uniformly, the concentrated load cantilever beam only considered for all the cases. The cantilever beam with a concentrated load at a distance of A from fixed support and uniformly distributed load throughout the span of the cantilever beam. And the third, next one is cantilever beam at a distance of A from fixed support, and cantilever beam with UDL is subjected to uniformly distributed load from free end support at a distance of at the span of A. And next case is that cantilever beam with couple at a free end. At a free end, its couple acted. And finally, cantilever beam subjected to uniformly varying load throughout the span of the beam. These are the cases we covered and calculated and derived the formula for those cases. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.